Light, both the force that makes the universe visible and the enigma that drives our understanding of reality. From the first flicker of a star to the glow of our own sun, light shapes everything we know. But what exactly is light, and how does it work? Tonight, we explore the fascinating nature of light, its behavior, its properties, and how it interacts with the universe. Imagine standing under a clear night sky, gazing up at countless stars scattered across the darkness. Each tiny point of light has traveled millions, sometimes billions of years to reach your eyes. The photons hitting your retina right now began their journey long before humans ever walked the earth. This is the incredible power of light, connecting us to the farthest reaches of space and time. Light surrounds us constantly, yet remains one of the most mysterious phenomena in the universe. It illuminates our world, enables us to see colors and shapes, and carries information from distant galaxies. Without light, there would be no warmth from the sun, no photosynthesis in plants, no vision, and no life as we know it. But light is far more than just illumination. It moves faster than anything else in the universe, travels through the vacuum of space without any medium, and behaves in ways that challenge our everyday understanding of reality. Sometimes it acts like a wave, rippling through space like vibrations on a pond. Other times, it behaves like tiny particles, each carrying packets of energy across vast distances. The story of light begins with the sun itself, our nearest star, a massive nuclear furnace, burning at temperatures of 15 million degrees Celsius. At its core, deep within the sun, hydrogen atoms fuse together to create helium, releasing tremendous amounts of energy in the process. This energy begins as high-energy gamma rays, but as it slowly works its way to the sun's surface over thousands of years, it transforms into the visible light that eventually reaches Earth. When you feel the warmth of sunlight on your skin or see the golden glow of sunrise, you are experiencing the end result of nuclear fusion that began in the sun's core long ago. The light touching you has traveled 93 million miles through the cold vacuum of space at a speed of 186,000 miles per second, taking just over 8 minutes to make the journey from sun to Earth. This same light that warms our planet also reveals the hidden secrets of the universe. When astronomers point their telescopes toward distant stars and galaxies, they are essentially time machines, collecting light that has been traveling for millions or billions of years. The light tells us about the temperature, composition, age, and motion of celestial objects, painting a picture of cosmic history written in wavelengths and frequencies. Every day, light performs countless invisible miracles around us. It enables plants to convert carbon dioxide and water into oxygen and sugar through photosynthesis, sustaining virtually all life on Earth. It allows our eyes to distinguish between millions of different colors and shades, creating the rich visual tapestry of our world. It bounces off surfaces, bends through lenses, and scatters through the atmosphere to create rainbows, sunsets, and the blue color of the sky. Yet despite its fundamental importance, light continues to puzzle scientists and philosophers alike. How can something travel so fast, yet have no mass? How can it behave as both a wave and a particle simultaneously? Why does it always travel at the same speed regardless of its source or destination? These questions have driven centuries of scientific investigation and continue to inspire new discoveries today. As we begin this journey into the nature of light, we will explore these mysteries and many more. We will discover how light travels through space, how it interacts with matter, and how it shapes our understanding of the universe itself. From the quantum realm of individual photons to the cosmic scale of distant galaxies, light serves as our guide to comprehending the fundamental workings of reality. So settle in comfortably as we embark on this illuminating adventure. Let the gentle glow of starlight above remind you that you are connected to the vast cosmos through the ancient language of light, a language that speaks of wonder, mystery, and the endless beauty of the universe that surrounds us all. To truly understand light, we must first recognize that it belongs to a much larger family of energy called electromagnetic radiation. This invisible spectrum extends far beyond what our eyes can detect, encompassing radio waves that carry our favorite songs across the airwaves, microwaves that heat our food, infrared radiation that we feel as warmth, the visible light that illuminates our world, ultraviolet rays that can tan or burn our skin, X-rays that reveal our bones, and gamma rays that emerge from the most energetic events in the universe. Think of electromagnetic radiation as a vast ocean of energy waves, with visible light representing just a tiny island in this enormous sea. All these different types of radiation are fundamentally the same phenomenon, differing only in their wavelength and frequency. Radio waves stretch out with wavelengths measured in meters or even kilometers, while gamma rays compress into wavelengths smaller than the nucleus of an atom. Visible light occupies a remarkably narrow band within this electromagnetic spectrum, spanning wavelengths from roughly 400 nanometers for violet light to 700 nanometers for red light. A nanometer is incredibly small, about 1/1,000,000th of a meter. To put this in perspective, if a nanometer were the size of a marble, then a marble would be the size of Earth itself. This tiny slice of the electromagnetic spectrum that we call visible light is what evolution has tuned our eyes to detect, and for good reason. Our sun emits most of its energy in this range, making it the most abundant form of electromagnetic radiation reaching Earth's surface. Water, which covers most of our planet and fills our bodies, is relatively transparent to visible light, allowing it to penetrate and sustain life in oceans, lakes, and rivers. But here lies one of the most profound mysteries in all of science. Light exhibits what physicists call wave-particle duality, meaning it behaves as both a wave and a particle depending on how we observe it. This concept challenges our everyday understanding of reality, because in our normal experience, things are either waves or particles, but never both simultaneously. When we think of waves, we might imagine ripples spreading across a pond after dropping a stone into the water. These waves have measurable properties like wavelength, the distance between successive crests, and frequency, the number of crests that pass a given point each second. Light exhibits these same wave-like properties. It can be reflected, refracted, and diffracted, just like water waves or sound waves. We can demonstrate light's wave nature through simple experiments. When light passes through two narrow slits placed close together, it creates an interference pattern on a screen behind the slits. This pattern consists of alternating bright and dark bands, exactly what we would expect if light were a wave. The bright bands occur where light waves from both slits arrive in phase, reinforcing each other, while the dark bands occur where the waves arrive out of phase, cancelling each other out. Yet light also behaves like a stream of particles, tiny packets of energy called photons. Each photon carries a specific amount of energy determined by the frequency of the light. Higher frequency light, like blue or violet, carries more energy per photon than lower frequency light, like red or infrared. This particle nature of light becomes apparent in phenomena like the photoelectric effect, where light striking a metal surface can knock electrons loose, but only if the light's frequency exceeds a certain threshold. Albert Einstein won the Nobel Prize in Physics in 1921 for explaining the photoelectric effect in terms of light particles, or photons. His work showed that light energy comes in discrete bundles rather than as a continuous stream. This was revolutionary because it meant that energy itself is quantized, coming in specific, indivisible amounts, rather than any arbitrary value. The dual nature of light means that photons are unlike anything in our everyday experience. They have no mass, yet they carry momentum. They always travel at the speed of light in a vacuum, yet they can have different energies depending on their frequency. They can behave like waves that interfere with each other, yet they can also be counted as individual particles. This wave-particle duality extends throughout the electromagnetic spectrum. Radio waves used in broadcasting behave primarily like waves, spreading out from antennas and traveling vast distances. At the other extreme, gamma rays from radioactive decay or cosmic events behave more like high-energy particles, each one packing enough energy to damage living cells or create spectacular light shows in our atmosphere. The electromagnetic spectrum tells us that visible light is just one note in a vast cosmic symphony of radiation. Radio telescopes detect the radio waves emitted by distant galaxies. revealing structures invisible to optical telescopes. Infrared telescopes peer through cosmic dust clouds to observe star formation in regions where visible light cannot penetrate. X-ray telescopes reveal the violent environments around black holes and neutron stars, where matter reaches temperatures of millions of degrees. Understanding light as electromagnetic radiation also helps explain many everyday phenomena. The warmth you feel from a campfire comes from infrared radiation, electromagnetic waves with slightly longer wavelengths than visible red light. The ultraviolet radiation from our sun, just beyond the violet end of the visible spectrum, is what causes sunburns and helps our bodies produce vitamin D. Even the microwave oven in your kitchen works by using electromagnetic radiation at a specific frequency that causes water molecules to vibrate and generate heat. The discovery of electromagnetic radiation fundamentally changed our understanding of the universe. Before the 19th century, scientists believed that light, heat, and electricity were completely separate phenomena. It was James Clerk Maxwell, a Scottish physicist, who first realized that these seemingly different forces were actually manifestations of the same underlying reality. In 1864, Maxwell published his famous equations that unified electricity and magnetism, showing that light itself was an electromagnetic wave. Maxwell's equations predicted that electromagnetic waves should travel at a specific speed, and when he calculated this speed, it matched exactly the known speed of light. This was no coincidence. Light, Maxwell realized, was simply electromagnetic radiation that happened to fall within the narrow range our eyes could detect. His equations also predicted the existence of electromagnetic radiation at frequencies far beyond what humans could see, opening up entirely new ways of exploring the universe. The electromagnetic spectrum extends across more than 20 orders of magnitude in frequency. At the lowest frequencies, we find extremely long radio waves that can stretch for thousands of kilometers. These waves can travel around the Earth by bouncing off the ionosphere, which is why AM radio stations can sometimes be heard from hundreds of miles away, especially at night when atmospheric conditions are favorable. Moving up in frequency, we encounter the radio waves used for FM broadcasting, television signals, and cell phone communications. These shorter radio waves travel in straight lines and cannot bend around the Earth's curvature, which is why FM radio has a more limited range than AM radio. The waves used for wireless internet, Bluetooth, and microwave ovens occupy an even higher frequency range, where the electromagnetic energy becomes intense enough to agitate water molecules and generate heat. Next comes infrared radiation, which we experience as heat. Every object with a temperature above absolute zero emits infrared radiation. This invisible light allows us to see in the dark using thermal cameras, and it's how we can feel the warmth of a fire or the sun on our skin, even when we're not directly touching the source. Infrared astronomy has revealed a hidden universe of cool stars, planet-forming disks, and cosmic dust clouds that remain invisible to ordinary telescopes. Then we reach the narrow band of visible light, spanning less than 1 octave in frequency. Within this tiny range, our eyes have evolved to distinguish millions of different colors and shades. The human visual system is remarkably sophisticated, containing 3 types of color-detecting cells that respond to different wavelengths of light. By comparing the signals from these cells, our brains can perceive colors that don't even exist as single wavelengths, such as magenta, which our minds create when both red and blue detecting cells are stimulated simultaneously. Beyond visible light lies ultraviolet radiation, which carries enough energy to break chemical bonds and cause sunburns. Many flowers have ultraviolet patterns invisible to human eyes but clearly visible to bees and other pollinators. Some birds can see ultraviolet light, giving them access to a visual world we can barely imagine. Ultraviolet astronomy reveals the hottest stars and the most energetic processes in the universe, from stellar coronas to the accretion disks around black holes. X-rays carry even more energy, enough to penetrate soft tissues but not dense materials like bones or metals. Medical X-ray imaging relies on this property, but X-rays also flood the universe from exotic sources like neutron stars and black holes. X-ray telescopes must be placed in space because Earth's atmosphere absorbs these high-energy photons before they can reach the ground. At the highest energies, we find gamma rays, electromagnetic radiation, so energetic that each photon can contain as much energy as a visible light photon multiplied by a billion times. Gamma rays are produced in the most violent events in the universe, from supernova explosions to the collision of neutron stars. When gamma rays interact with Earth's atmosphere, they create cascades of secondary particles that can be detected by specialized telescopes, giving us glimpses into the most extreme environments in the cosmos. The wave nature of light becomes most apparent when we consider how it propagates through space. Unlike sound waves, which require air or another medium to travel through, electromagnetic waves can travel through the perfect vacuum of space. They consist of oscillating electric and magnetic fields that regenerate each other as they move, creating a self-sustaining disturbance that can travel across the universe without any supporting medium. When light behaves as a wave, it exhibits all the properties we associate with waves. It can be reflected when it bounces off a surface, refracted when it bends while passing from one medium to another, and diffracted when it spreads out after passing through a narrow opening. Light waves can also interfere with each other, creating patterns of constructive and destructive interference that produce the colors in soap bubbles, oil slicks, and peacock feathers. Yet the particle nature of light is equally real and important. Photons are massless particles that always travel at the speed of light. They carry both energy and momentum, even though they have no mass. When a photon is absorbed by an atom, it can cause an electron to jump to a higher energy level. When an electron falls back to a lower energy level, it emits a photon with energy exactly equal to the difference between the two levels. This quantized nature of light energy explains why different elements emit and absorb light at specific wavelengths. When we heat sodium, it glows with a characteristic yellow-orange color because electrons in sodium atoms can only transition between specific energy levels, producing photons of very particular energies. This is how we can determine the composition of distant stars by analyzing the light they emit, a technique called spectroscopy that has revolutionized our understanding of the universe. The wave-particle duality of light represents one of the most profound insights in the history of science. It tells us that our everyday intuitions about the nature of reality break down at the fundamental level. Light is neither simply a wave nor simply a particle, but something more complex that can manifest as either depending on how we choose to observe it. This strange behavior extends to all forms of electromagnetic radiation. Radio waves, despite their wave-like behavior in antennas and receivers, are still composed of individual photons. Gamma rays, despite their particle-like interactions with matter, still exhibit wave properties like interference and diffraction. The entire electromagnetic spectrum represents a unified phenomenon that bridges the gap between our classical understanding of waves and particles. As we delve deeper into the nature of light, we begin to see that it serves as a bridge between the quantum world of atoms and particles and the cosmic scale of stars and galaxies. Light connects the smallest and largest structures in the universe, carrying information and energy across space and time in ways that continue to amaze and inspire scientists around the world. Light is both a wave and a particle, but how can something be both? This dual nature is at the heart of the mysteries we aim to unravel as we continue our journey into understanding how light actually works. The speed of light in a vacuum is exactly 299,792,458 meters per second, or roughly 300,000 kilometers per second. This number represents far more than just how fast light travels. It is woven into the very fabric of space and time itself, serving as the ultimate speed limit for everything in the universe, and fundamentally shaping how reality works at its deepest level. To truly appreciate the significance of light's speed, we must first understand just how incredibly fast it really is. Light can circle the entire Earth more than 7 times in a single second. It can travel from Earth to the Moon in just 1 1/3 seconds, a journey that took the Apollo astronauts 3 days to complete. Light from our Sun takes 8 minutes and 20 seconds to reach Earth, meaning that when you look at the Sun, you are seeing it as it appeared over 8 minutes ago. This incredible speed was not always known to science. For centuries, many philosophers and scientists believed that light traveled instantaneously, appearing everywhere at once the moment it was created. The first serious attempt to measure light's speed came from the Italian scientist Galileo Galilei in the early 1600s. He and an assistant stood on hilltops several kilometers apart, each holding a lantern. Galileo would uncover his lantern, and his assistant was supposed to uncover his own lantern the moment he saw Galileo's light. By measuring the time delay, Galileo hoped to calculate light's speed. However, the distances were far too small, and human reaction times far too slow to detect light's incredible velocity. The first successful measurement of light speed came from an unexpected source, the moons of Jupiter. In 1676, the Danish astronomer Ole Rømer was studying Io, one of Jupiter's largest moons, as it orbited the giant planet. Rømer noticed that the timing of Io's eclipses behind Jupiter seemed to change depending on Earth's position in its orbit around the Sun. When Earth was moving toward Jupiter, the eclipses appeared to happen slightly earlier than predicted. When Earth was moving away from Jupiter, the eclipses appeared to happen slightly later. Rømer realized that this timing difference was caused by the finite speed of light. When Earth was closer to Jupiter, light from Io had less distance to travel, so the eclipses appeared to happen sooner. When Earth was farther from Jupiter, light had more distance to travel, causing the eclipses to appear delayed. By measuring these timing differences and knowing the distances involved, Rømer calculated that light traveled at approximately 200,000 kilometers per second, remarkably close to the true value, considering the limitations of 17th century astronomy. Over the following centuries, increasingly sophisticated methods were developed to measure light speed with greater precision. In 1849, the French physicist Hippolyte Fizeau used a rotating toothed wheel to chop a beam of light into pulses, then measured how fast the wheel had to spin for the returning light to pass through the gaps between the teeth. This ingenious experiment yielded a value very close to the true speed of light. Albert Michelson, an American physicist, devoted much of his career to measuring light speed with unprecedented accuracy. Using rotating mirrors and precisely measured distances, Michelson refined the measurement of light speed to within a few kilometers per second of the true value. His work was so precise that he became the first American to win a Nobel Prize in Physics, awarded in 1907 for his optical precision instruments and spectroscopic investigations. But the true significance of light speed became clear only with Albert Einstein's special theory of relativity, published in 1905. Einstein realized that the speed of light in a vacuum is not just very fast, it is absolutely constant for all observers, regardless of their motion. This seemingly simple statement has profound implications that revolutionized our understanding of space and time. According to Einstein's theory, nothing with mass can ever reach the speed of light, no matter how much energy is applied. As an object approaches light speed, its mass effectively increases toward infinity, requiring infinite energy to accelerate it further. This creates an absolute speed limit for the universe. Massless particles like photons always travel at exactly the speed of light, never faster or slower. The constancy of light's speed leads to some of the most counterintuitive predictions in all of physics. Time dilation means that time passes more slowly for objects moving at high speeds relative to a stationary observer. If you could travel at 99% the speed of light, time would pass about 7 times more slowly for you compared to someone at rest. A journey that takes you 1 year would appear to take 7 years to outside observers. Length contraction is another consequence of light's constant speed. Objects appear to shrink in the direction of their motion as they approach light speed. At 99% light speed, an object would appear to contract to about 14% of its original length, as measured by a stationary observer. However, the traveler would not notice any change in their own dimensions. These effects are not just theoretical curiosities. They have been confirmed in countless experiments and are essential for the operation of technologies we use every day. The Global Positioning System, or GPS, must account for both time dilation and gravitational effects on time to maintain accuracy. Without these relativistic corrections, GPS would accumulate errors of several kilometers per day, making it useless for navigation. The speed of light also defines the relationship between energy and mass through Einstein's famous equation E equals mc squared. This equation tells us that mass and energy are interchangeable, with the speed of light squared serving as the conversion factor. Even a tiny amount of mass contains an enormous amount of energy. The energy in a single gram of matter, if completely converted to energy, would be equivalent to the explosion of over 20,000 tons of TNT. This mass-energy equivalence explains how stars generate their incredible power. In the core of our Sun, hydrogen nuclei fuse together to form helium, converting a small amount of mass into energy. The Sun converts about 4 million tons of mass into energy every second, yet this represents only a tiny fraction of its total mass. The energy travels outward from the Sun's core, eventually reaching the surface and radiating into space as light and heat. The speed of light also determines how we perceive the universe around us. When we look at distant objects, we are literally looking back in time. The nearest star to our Sun, Proxima Centauri, is about 4¼ light-years away, meaning its light takes 4¼ years to reach us. When we observe this star, we see it as it appeared over 4 years ago. More distant objects show us even older light. The Andromeda Galaxy, our nearest galactic neighbor, is about 2.5 million light-years away, so we see it as it appeared 2.5 million years ago. This light travel time creates what astronomers call the observable universe, the region of space from which light has had time to reach us since the beginning of the universe. The observable universe extends about 46 billion light-years in all directions, even though the universe is only about 13.8 billion years old. This apparent contradiction arises because space itself has been expanding during the time light has been traveling toward us. The cosmic microwave background radiation, detected by radio telescopes, represents the oldest light in the universe. This radiation was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this time, the universe was opaque to light, filled with a hot plasma that absorbed and scattered photons. The cosmic microwave background gives us a snapshot of the universe as it appeared during this cosmic dawn. Light's finite speed also affects how we communicate across the solar system. Radio signals to Mars can take between 4 and 24 minutes to arrive, depending on the planet's positions in their orbits. This delay makes real-time conversation impossible and requires careful planning for robotic missions to distant planets. Commands sent to spacecraft must be planned well in advance, and mission controllers must wait long periods to receive confirmation that their instructions have been received and executed. The speed of light serves as more than just a speed limit. It represents a fundamental property of space-time itself. In Einstein's theory of general relativity, massive objects curve space-time, and this curvature affects how light travels. Light always follows the shortest path through curved space-time, which may appear curved to distant observers. This bending of light by gravity has been confirmed in numerous observations, from the deflection of starlight during solar eclipses to the gravitational lensing of distant galaxies by intervening clusters of matter. Quantum mechanics adds another layer of mystery to light's behavior. While individual photons always travel at the speed of light, the information carried by light can sometimes appear to travel faster or slower than c through certain materials or under special conditions. However, these effects never violate the fundamental principle that no information can be transmitted faster than light in a vacuum. The speed of light is not just a number, it is a constant that shapes the fabric of the universe, acting as a boundary for space and time. It determines how we perceive reality, how energy and matter relate to each other, and how information propagates throughout the cosmos. As we continue our exploration of light, we will see how this universal speed limit influences every aspect of how light travels and interacts with the world around us. Light travels as a wave, rippling through the universe in ways that seem almost magical. Unlike the waves we see on the ocean or the sound waves that carry music to our ears, light waves require no medium to travel through. They consist of oscillating electric and magnetic fields that dance together in perfect harmony, creating a self-sustaining disturbance that can journey across billions of light-years of empty space without losing its fundamental character. To understand how light waves work, imagine throwing a stone into a perfectly still pond. Ripples spread outward in concentric circles, carrying energy away from the point of impact. Each ripple has a wavelength, the distance from one crest to the next, and a frequency, the number of crests that pass a given point each second. Light waves behave similarly, but instead of disturbing water, they create oscillations in the invisible fields that permeate all of space. An electromagnetic wave consists of two components that are intimately connected. The electric field oscillates in one direction, while the magnetic field oscillates in a perpendicular direction. These two fields regenerate each other as the wave travels, with the changing electric field creating the magnetic field, and the changing magnetic field creating the electric field. This mutual creation allows the wave to sustain itself indefinitely, traveling through the vacuum of space without any supporting material. The relationship between the electric and magnetic fields in a light wave is governed by the same equations that James Clerk Maxwell discovered in the 1860s. These equations show that the two fields must oscillate at exactly the same frequency and must be perfectly synchronized. When the electric field reaches its maximum strength, the magnetic field is also at its maximum. When one field passes through zero, the other does as well. This perfect coordination is what allows electromagnetic waves to propagate through empty space. The wavelength of light determines many of its most important properties. Visible light spans wavelengths from about 400 nanometers for deep violet to 700 nanometers for deep red. To put these incredibly small distances in perspective, it would take about 2,500 red light waves placed end to end to equal the thickness of a human hair. Despite their tiny size, these wavelength differences are what create all the colors we see in the world around us. Frequency and wavelength are inversely related through light speed. As wavelength increases, frequency decreases, and vice versa. Red light has a longer wavelength and lower frequency than blue light. This relationship means that red light carries less energy per photon than blue light, which is why red lights are often used in darkrooms for developing photographs. The lower energy red photons are less likely to trigger the chemical reactions in photographic film. When light waves encounter obstacles or openings comparable to their wavelength, they exhibit a phenomenon called diffraction. Light waves can bend around corners, spread out after passing through narrow openings, and create complex interference patterns. This wave behavior is why you can sometimes see faint light around the edges of shadows, and why looking at a bright light through a fine mesh or fabric creates intricate patterns of light and dark. The wave nature of light becomes particularly evident when two or more light waves interact with each other. When waves from different sources meet, they can either reinforce each other or cancel each other out, depending on their relative phases. This interference can create spectacular displays of color and pattern, from the iridescent shimmer of soap bubbles to the brilliant hues of butterfly wings. Constructive interference occurs when two waves arrive at the same point, with their crests and troughs aligned. The waves add together, creating a combined wave with greater amplitude than either original wave. This is why laser light can be so intense. In a laser, billions of light waves oscillate in perfect synchronization, all reinforcing each other to create an incredibly bright, focused beam. Destructive interference happens when waves arrive with their crests aligned with the troughs of other waves. The waves cancel each other out, creating regions of darkness even when multiple light sources are present. This phenomenon is used in noise-canceling headphones, where sound waves are deliberately created to cancel out unwanted noise, and it also explains some of the dark bands in interference patterns created by light. The wave properties of light allow it to be focused, dispersed, and manipulated in countless ways. Lenses work by bending light waves as they pass from air into glass and back into air. The curved surfaces of lenses cause different parts of a light wave to travel slightly different distances, effectively reshaping the wavefront. A converging lens brings parallel light waves to a focus, while a diverging lens spreads them out. Prisms demonstrate another wave property of light called dispersion. White light contains waves of many different wavelengths mixed together. When this light enters a prism, waves of different wavelengths bend by different amounts, because the glass has a slightly different refractive index for each wavelength. This separates the white light into its component colors, creating the familiar spectrum from red through violet. The wave nature of light also explains how it can travel such vast distances through space without losing coherence. Unlike material waves, which gradually lose energy to friction and other dissipative processes, electromagnetic waves in vacuum experience no such losses. A light wave from a distant star maintains its fundamental wave characteristics throughout its journey of millions or billions of years, arriving at Earth with its frequency and wavelength unchanged from when it was first emitted. Polarization is another distinctly wave-like property of light. While light waves oscillate perpendicular to their direction of travel, they can oscillate in any direction within that perpendicular plane. Unpolarized light, like that from the sun or an incandescent bulb, contains waves oscillating in all possible directions. Polarized light has waves that oscillate in only one specific direction. Many natural phenomena create polarized light. When sunlight reflects off water, glass, or other smooth surfaces, it becomes partially polarized. This is why polarized sunglasses can dramatically reduce glare from these surfaces. The polarizing filter blocks light waves oscillating in the direction of the glare, while allowing waves oscillating in other directions to pass through. Light waves can also become polarized when they scatter off small particles in the atmosphere. This is why the sky appears blue and why the light from the sky is partially polarized. Bees and other insects can detect this polarization and use it for navigation, even on overcast days when the sun is not directly visible. The wave theory of light successfully explains countless phenomena, from the colors in oil slicks to the operation of radio telescopes. When light waves reflect off the top and bottom surfaces of a thin oil film, they create interference patterns that produce brilliant colors. The specific colors depend on the thickness of the film and the angle at which you view it, which is why oil slicks shimmer with changing hues as you move. Radio telescopes work by collecting and focusing radio waves, which are simply light waves with much longer wavelengths than visible light. These instruments can be enormous, with some spanning many kilometers, because radio wavelengths are much larger than optical wavelengths. The largest radio telescope, the 500-meter Aperture Spherical Telescope in China, uses a dish 500 meters in diameter to collect faint radio waves from distant cosmic sources. Wave interference also plays a crucial role in modern technology. Holography uses the interference between a reference beam and light scattered from an object to record not just the intensity of light, but also its phase information. This allows a hologram to reconstruct a complete three-dimensional image with proper depth and parallax effects. Fiber optic communications rely on the wave properties of light to carry information across vast distances. Light waves traveling through optical fibers can maintain their coherence over hundreds of kilometers, allowing high-speed internet and telephone signals to span continents with minimal loss of signal quality. The waves are guided through the fiber by total internal reflection, bouncing back and forth within the core while maintaining their wave properties. The wave nature of light even affects how we see everyday objects. The colors of objects depend on which wavelengths of light they reflect, absorb, or transmit. A red rose appears red because its petals contain pigments that absorb most wavelengths of visible light, while reflecting predominantly red wavelengths back to our eyes. The wave properties of this reflected light, including its wavelength and intensity, determine the specific shade and brightness of red that we perceive. Understanding light as a wave helps explain many of the most beautiful phenomena in nature. Rainbows form when sunlight encounters millions of tiny water droplets in the air. Each droplet acts like a tiny prism, dispersing white light into its component wavelengths. The different wavelengths emerge from each droplet at slightly different angles, creating the familiar arc of colors across the sky. The blue color of the sky results from the wave property called Rayleigh scattering. Shorter wavelength blue light is scattered more strongly by the small molecules in Earth's atmosphere than longer wavelength red light. This causes blue light to bounce around the sky in all directions, giving the entire sky its blue appearance during the day. At sunrise and sunset, when sunlight must travel through more atmosphere to reach us, most of the blue light has been scattered away, leaving the longer wavelength reds and oranges to color the horizon. Light travels as a wave, rippling through the universe. But what happens when these waves interact with matter? The answer to this question reveals even more fascinating aspects of light's behavior and leads us deeper into understanding how light shapes the world around us. When light encounters different materials and surfaces, it transforms in remarkable ways that reveal the hidden beauty and complexity of our world. These interactions between light and matter create the colors we see, the images we observe, and the spectacular natural phenomena that have inspired wonder and scientific investigation for centuries. Reflection is perhaps the most familiar way that light interacts with surfaces. When light waves strike a smooth surface like a mirror, they bounce back in a predictable pattern, governed by a simple but profound rule known as the law of reflection. This law states that the angle at which light approaches a surface, called the angle of incidence, exactly equals the angle at which it bounces away, called the angle of reflection. Both angles are measured from an imaginary line perpendicular to the surface called the normal. This law of reflection explains why we can see ourselves in mirrors and why the reflection appears to be the same distance behind the mirror as we stand in front of it. When you look at yourself in a bathroom mirror, light from your face travels to the mirror, reflects according to this law, and then travels to your eyes. Your brain interprets this reflected light as coming from a virtual image located behind the mirror surface. But not all surfaces reflect light in the same way. Smooth surfaces like mirrors, still water, or polished metal create what scientists call specular reflection, where light rays remain parallel after reflection and create clear, sharp images. Rough surfaces like paper, concrete, or tree bark create diffuse reflection, where light rays scatter in many different directions. This diffuse reflection is actually what allows us to see most objects around us. Without it, only mirrors and other highly polished surfaces would be visible. The roughness that determines whether reflection is specular or diffuse depends on the wavelength of light. A surface that appears smooth to visible light might seem rough to much shorter wavelength ultraviolet light. This is why some materials that look smooth and shiny to our eyes don't reflect ultraviolet light very well. Conversely, surfaces that seem rough to visible light can still create good reflections for much longer wavelength radio waves. Refraction occurs when light travels from one transparent material into another with a different density. As light waves pass from air into water, glass, or any other transparent medium, they change direction in a process that has fascinated observers since ancient times. This bending of light follows Snell's law, discovered by the Dutch mathematician Willebrord Snellius in 1621. Snell's law relates the angles and speeds of light in different materials through a property called the refractive index. Each transparent material has a characteristic refractive index that describes how much it slows down light compared to the speed of light in vacuum. Air has a refractive index very close to 1, meaning light travels through it at nearly the same speed as in vacuum. Water has a refractive index of about 1.33, meaning light travels about 25% slower in water than in air. Glass typically has a refractive index between 1.5 and 1.9, depending on its composition. When light passes from a material with a lower refractive index to one with a higher refractive index, it bends toward the normal, the imaginary perpendicular line to the surface. When light passes from a higher to lower refractive index material, it bends away from the normal. This bending is what makes a straight stick appear bent when partially submerged in water, and why swimming pools appear shallower than they actually are. The amount of bending depends on both the difference in refractive indices and the angle at which light approaches the interface between materials. Light that strikes perpendicular to the surface passes through without bending, while light at steeper angles experiences more dramatic changes in direction. This angle dependence is why objects underwater appear to shift position as you move your viewing angle. Refraction has countless practical applications in our daily lives. Eyeglasses and contact lenses use carefully shaped pieces of glass or plastic to bend light in precise ways that correct vision problems. Cameras use complex systems of multiple lenses to focus light and create sharp images on film or digital sensors. Microscopes and telescopes employ sophisticated combinations of lenses and mirrors to magnify distant or tiny objects far beyond what our naked eyes could see. One of the most spectacular consequences of refraction is total internal reflection, which occurs when light tries to pass from a material with a higher refractive index to one with a lower refractive index at too steep an angle. Instead of partially passing through and partially reflecting, all the light reflects back into the original material. This phenomenon is what allows optical fibers to guide light around corners and across vast distances with minimal loss. Fiber optic cables use total internal reflection to trap light inside thin strands of glass. Light enters one end of the fiber and bounces back and forth off the walls as it travels down the length of the cable. Even if the fiber is bent or curved, the light remains trapped inside, allowing information to be transmitted as pulses of light over thousands of kilometers with remarkable efficiency. Dispersion reveals perhaps the most beautiful aspect of light's interaction with matter. This phenomenon occurs because different wavelengths of light bend by different amounts when passing through transparent materials. Most materials have slightly different refractive indices for different colors, causing white light to separate into its component wavelengths when it passes through a prism or other dispersive element. Isaac Newton first systematically studied dispersion in the 1660s, when he allowed sunlight to pass through a triangular glass prism. He observed that the white light separated into a spectrum of colors, from red through orange, yellow, green, blue, indigo, to violet. Newton called this band of colors a spectrum, from the Latin word meaning to look or appearance. The reason for dispersion lies in how light waves interact with the atoms in transparent materials. Shorter wavelength blue and violet light interact more strongly with the electrons in glass atoms than longer wavelength red light. This stronger interaction causes blue light to slow down more than red light, resulting in a larger refractive index for blue light. When white light enters a prism, the blue light bends more sharply than the red light, spreading the colors out into a visible spectrum. Dispersion creates many of the most beautiful natural phenomena we observe. Rainbows form when sunlight encounters countless tiny water droplets suspended in the air after a rainstorm. Each droplet acts as a miniature prism, refracting sunlight as it enters, reflecting it off the back surface, and refracting it again as it exits. The different colors emerge from each droplet at slightly different angles, creating the spectacular arc of colors we see across the sky. The precise geometry of rainbow formation explains why rainbows always appear as circles centered on the point directly opposite the sun from your perspective. You typically see only the upper half of this circle because the ground blocks the lower portion, but from an airplane or high mountain, you might glimpse a complete circular rainbow. The primary rainbow shows red on the outside and violet on the inside, while a fainter secondary rainbow sometimes appears above the primary with colors in reverse order. Atmospheric dispersion also explains why the sun appears reddish at sunrise and sunset. When the sun is low on the horizon, its light must travel through much more atmosphere to reach your eyes. The atmosphere scatters shorter wavelength blue light more strongly than longer wavelength red light, gradually removing the blue light from the direct sunbeam as it travels through more and more air. By the time the light reaches you, most of the blue light has been scattered away, leaving predominantly red and orange wavelengths to color the sun and surrounding sky. This same scattering effect makes the sky appear blue during the day. Blue light is scattered in all directions by the tiny molecules in Earth's atmosphere, creating a diffuse blue glow that fills the entire sky. This phenomenon, called Rayleigh scattering, is strongest for the shortest visible wavelengths, which is why the sky appears blue rather than green or yellow. Dispersion plays a crucial role in modern technology and scientific instruments. Spectrometers use prisms or diffraction gratings to separate light into its component wavelengths, allowing scientists to analyze the composition of materials, stars, and even distant galaxies. By studying which wavelengths are absorbed or emitted by different substances, researchers can identify elements and compounds with remarkable precision. The chromatic aberration that results from dispersion was a major problem for early telescope and microscope makers. Different colors focus at slightly different distances, creating blurry, rainbow-edged images. Modern optical instruments use combinations of different types of glass with carefully matched dispersion properties to minimize these effects, creating crisp, clear images across the entire visible spectrum. Diamonds and other precious gems owe much of their brilliance to dispersion. The high refractive index of diamond causes light to bend sharply when entering and exiting the stone. Combined with careful cutting that maximizes total internal reflection, this creates the characteristic sparkle and fire that makes diamonds so prized. The fire refers specifically to the flashes of colored light that result from dispersion as white light separates into its component colors within the gem. Even everyday objects demonstrate the effects of dispersion. The slight rainbow edge you might notice around bright lights when looking through window glass results from chromatic aberration. Soap bubbles and oil slicks show brilliant colors due to interference between light waves reflecting from different surfaces. But dispersion also plays a role in determining which colors are most prominent at different viewing angles. Understanding reflection, refraction, and dispersion helps us appreciate the incredible complexity hidden within seemingly simple interactions between light and matter. These phenomena work together to create the rich visual world we experience every day, from the clear images in our cameras and eyeglasses to the spectacular colors of sunsets and rainbows. When light strikes a surface, it doesn't just bounce or bend, it transforms. It reveals the richness of the world around us, from the gentle glow of a sunset to the vibrant colors of a prism. These transformations of light as it interacts with matter lead us to an even deeper understanding of light's true nature as both wave and particle. Light is not just a wave rippling through space, it is also a stream of particles, tiny packets of energy called photons, that carry the fundamental forces of electromagnetism across the universe. These remarkable particles have no mass, yet they possess energy and momentum. They always travel at the speed of light, yet they can carry vastly different amounts of energy depending on their frequency. Understanding photons reveals one of the most profound mysteries in physics and opens our eyes to the quantum nature of reality itself. The concept of light as particles emerged from one of the most puzzling discoveries in early 20th century physics. When scientists began studying how light interacts with metals, they discovered phenomena that the wave theory of light simply could not explain. The photoelectric effect, first observed by Heinrich Hertz in 1887, showed that shining light on certain metals could knock electrons loose from their surface, creating an electric current. Initially, scientists expected that brighter light would knock out electrons with more energy, just as larger ocean waves carry more energy than smaller ones. But experiments revealed something completely unexpected. The energy of the ejected electrons depended only on the color or frequency of the light, not on its brightness. Dim blue light could knock out high-energy electrons, while bright red light might not eject any electrons at all, regardless of how intense it was. This mysterious behavior puzzled physicists for nearly 2 decades, until Albert Einstein proposed a revolutionary explanation in 1905. Einstein suggested that light itself comes in discrete packets of energy, which we now call photons. Each photon carries a specific amount of energy determined by the frequency of the light. Higher frequency light, like blue or ultraviolet, carries more energy per photon than lower frequency light, like red or infrared. Einstein's photon theory explained the photoelectric effect perfectly. When a photon strikes an electron in the metal, it transfers all of its energy to that single electron in one instantaneous transaction. If the photon carries enough energy to overcome the forces holding the electron to the metal, the electron escapes. If not, nothing happens, regardless of how many low-energy photons are present. This all-or-nothing behavior is fundamentally different from what we would expect if light were purely a wave. The energy of each photon is determined by Planck's constant, multiplied by the frequency of the light. Max Planck had introduced this constant in 1900 to explain the spectrum of light emitted by hot objects, but Einstein was the first to realize its deeper significance for the nature of light itself. Planck's constant is an incredibly tiny number, which is why the particle nature of light is not obvious in everyday experience. It takes enormous numbers of photons to create even the faintest visible light. To appreciate just how small individual photons are, consider that a typical laser pointer emits about 1 million billion photons every second. Even the faintest star visible to the naked eye sends about 100 photons per second into your eye. Your eye is so sensitive that it can detect as few as 5 to 10 photons arriving within a fraction of a second, making it one of the most sensitive light detectors ever created. Each photon is truly indivisible. Unlike a wave, which can be partially absorbed or reflected, a photon must be either completely absorbed or not absorbed at all. When an atom absorbs a photon, the photon disappears entirely, transferring all of its energy to the atom. This quantum behavior means that energy transfers in the microscopic world happen in discrete jumps, rather than smooth, continuous changes. The particle nature of photons explains many phenomena that puzzled early scientists. Fluorescence occurs when atoms absorb high-energy photons and then emit lower-energy photons. A fluorescent material might absorb invisible ultraviolet photons and emit visible light photons. Since energy must be conserved, the emitted photons always carry less energy than the absorbed photons, with the difference appearing as heat in the material. Phosphorescence works similarly, but with a delay. The absorbing atoms enter an excited state that can persist for minutes, hours, or even years before finally emitting a photon. This is why glow-in-the-dark materials can continue shining long after the lights are turned off. The atoms slowly release the energy they absorbed earlier, one photon at a time. The momentum carried by photons, despite their lack of mass, explains how light can exert physical forces. Radiation pressure from sunlight is what pushes the tails of comets away from the sun, creating the spectacular displays we see when these cosmic visitors approach our solar system. Solar sails on spacecraft use this same radiation pressure for propulsion, allowing vehicles to travel through space using only the momentum of photons from the sun. Photons also play a crucial role in all chemical processes involving light. Photosynthesis, the process that sustains virtually all life on Earth, begins when chlorophyll molecules absorb individual photons of sunlight. Each absorbed photon provides exactly the right amount of energy to excite an electron in the chlorophyll, starting a complex series of chemical reactions that ultimately convert carbon dioxide and water into sugar and oxygen. The human visual system has evolved to detect individual photons with remarkable efficiency. The rod cells in our retinas can respond to single photons, though our brain requires several photons arriving within a short time window before we consciously perceive light. This incredible sensitivity allows us to see stars whose light has traveled billions of years to reach us, with only a handful of photons per second entering our eyes. Digital cameras and other electronic light detectors work by converting individual photons into electrical signals. In a camera sensor, each photon that strikes the detector knocks loose an electron, creating a tiny electric charge. The camera counts these charges to measure how many photons arrived at each point on the sensor, building up the digital image one photon at a time. The particle nature of light becomes especially important in quantum mechanics, where photons serve as the fundamental carriers of electromagnetic force. When two electrically charged particles interact, they do so by exchanging photons. These virtual photons, as they are called, carry the electromagnetic force between particles, creating attractions and repulsions that hold atoms together and govern all chemical and biological processes. Lasers demonstrate the remarkable properties of photons in a dramatic way. In a laser, billions of atoms are stimulated to emit photons in perfect synchronization. All these photons have exactly the same energy, travel in exactly the same direction, and oscillate in perfect phase with each other. This creates an incredibly intense, focused beam of light that can cut through steel, perform delicate eye surgery, or carry information through fiber optic cables. The process that makes lasers work, called stimulated emission, occurs when a photon encounters an atom in an excited state. Instead of being absorbed, the photon stimulates the atom to emit an identical photon, doubling the number of photons. In a laser, this process cascades through billions of atoms, creating an avalanche of identical photons that emerges as the laser beam. Quantum entanglement, one of the strangest phenomena in physics, can occur between pairs of photons. When two photons are entangled, measuring the properties of one photon instantly affects the properties of the other, regardless of how far apart they are. Einstein called this spooky action at a distance, but experiments have confirmed that entangled photons really do exhibit this mysterious connection. The energy quantization of photons explains why heated objects glow with specific colors. As temperature increases, atoms vibrate more energetically and emit photons with higher energies. A cool object emits mostly infrared photons that we feel as heat but cannot see. As it gets hotter, it begins to emit red photons, then orange, yellow, and eventually blue and white as the temperature continues to rise. This is why stars of different temperatures appear as different colors to our eyes. X-ray and gamma-ray photons carry so much energy that they can break apart molecules and damage living tissue. This is why these forms of electromagnetic radiation are dangerous to humans, but it also makes them useful for medical imaging and cancer treatment. Each X-ray photon carries thousands of times more energy than a visible light photon, giving it the ability to penetrate deep into the human body. At the other extreme, radio wave photons carry very little energy each. It takes trillions of radio photons to equal the energy of a single visible light photon. This is why radio telescopes must be so large and sensitive to detect the faint radio signals from distant astronomical sources. Despite their low individual energies, radio photons can still carry information across vast distances, enabling communication with spacecraft throughout the solar system. The discovery of photons revolutionized our understanding of light and led to the development of quantum mechanics, one of the most successful theories in the history of science. Photons bridge the gap between the familiar world of everyday experience and the strange quantum realm where particles can be in multiple states simultaneously and distant objects can influence each other instantaneously. Modern technology depends heavily on our understanding of photons. Light-emitting diodes or LEDs work by forcing electrons to combine with holes in a semiconductor, emitting photons in the process. Solar panels work in reverse, using photons to knock electrons loose and create electric current. Photomultiplier tubes can detect individual photons and amplify their signals, enabling astronomers to study the faintest objects in the universe. The wave-particle duality of light means that photons exhibit both particle and wave properties simultaneously. They can interfere with each other like waves, creating the beautiful patterns we see in soap bubbles and oil slicks. Yet they also behave like discrete particles, carrying specific amounts of energy and momentum from place to place throughout the universe. Light is not just a wave, it is a stream of particles, each carrying energy, interacting with the world in ways we are only beginning to understand. These photons connect us to the quantum foundation of reality, revealing that even the most familiar phenomena in our daily lives operate according to the strange and wonderful rules of quantum mechanics. The world is awash with color, but it is light that creates the palette, painting everything we see. Each color tells a story, a message encoded in the wavelength of light that reveals the hidden properties of matter and energy throughout the universe. What we perceive as color is actually our brain's interpretation of different wavelengths of electromagnetic radiation, a narrow slice of the vast spectrum that surrounds us, but remains largely invisible to our eyes. The visible spectrum spans a remarkably small range of wavelengths, from approximately 400 nanometers at the violet end to 700 nanometers at the red end. This represents less than 1% of the entire electromagnetic spectrum, yet within this tiny window lies all the color and visual beauty we experience in our daily lives. Evolution has fine-tuned our eyes to detect precisely this range, because it encompasses the wavelengths where our sun emits most of its energy and where Earth's atmosphere is most transparent. At the shortest visible wavelengths, we find violet light, carrying the highest energy among visible photons. Violet light has a wavelength of about 400 to 450 nanometers and appears at the very edge of what our eyes can detect. Beyond violet lies ultraviolet radiation, invisible to humans but detectable by many insects, birds, and marine animals. Some flowers display intricate ultraviolet patterns that guide pollinating bees to their nectar, creating a hidden world of color and design completely invisible to human eyes. Moving to longer wavelengths, we encounter blue light, ranging from about 450 to 495 nanometers. Blue light carries considerable energy and plays important roles in biological processes. It helps regulate our circadian rhythms, the internal clocks that control our sleep-wake cycles. Exposure to blue light during the day helps keep us alert and awake, while reducing blue light exposure in the evening allows our bodies to prepare for sleep by producing melatonin. Green light occupies the center of the visible spectrum, spanning wavelengths from about 495 to 570 nanometers. Our eyes are most sensitive to green light, which is why night vision devices often use green displays and why green laser pointers appear brighter than red ones of the same power. This sensitivity to green light makes evolutionary sense, as it allows us to distinguish subtle variations in vegetation, an important skill for our ancestors who depended on plants for food and shelter. Yellow light bridges the gap between green and orange, with wavelengths from about 570 to 590 nanometers. Interestingly, we can perceive yellow in two completely different ways. True yellow light consists of photons with wavelengths in this range, but we also see yellow when our eyes simultaneously detect red and green light with no yellow wavelengths present. This demonstrates that color perception is not simply a direct measurement of wavelength, but a complex interpretation performed by our brains. Orange light spans wavelengths from about 590 to 620 nanometers, while red light extends from 620 nanometers to the limits of human vision at around 700 nanometers. Red light carries the least energy among visible photons and can penetrate through materials that block shorter wavelengths. This is why red lights are used in darkrooms for developing photographs, and why red light is less likely to disturb night vision. Beyond red light lies infrared radiation, which we feel as heat but cannot see. Many animals, including snakes, can detect infrared radiation, allowing them to hunt warm-blooded prey in complete darkness. Thermal cameras reveal the infrared world around us, showing the heat signatures of living creatures and warm objects as glowing shapes against cooler backgrounds. The perception of color depends not just on the wavelength of light, but also on the remarkable structure and function of the human eye. Our retinas contain 3 types of cone cells, each most sensitive to different wavelengths of light. Short wavelength cones respond primarily to blue light, medium wavelength cones to green light, and long wavelength cones to red light. Our brains compare the signals from these 3 types of cones to determine what colors we perceive. This 3-color system allows us to see millions of different hues and shades, far more than the simple sequence of spectral colors might suggest. Colors like magenta, pink, brown, and cyan have no single corresponding wavelength in the spectrum. Instead, they result from specific combinations of wavelengths that stimulate our cone cells in particular ways. Magenta, for example, appears when both our red and blue sensitive cones are stimulated while our green sensitive cones receive little input. Color blindness occurs when one or more types of cone cells are missing or function improperly. The most common form, red-green color blindness, affects about 8% of men and less than 1% of women. People with this condition have difficulty distinguishing between certain shades of red and green because their cone cells cannot properly differentiate between these wavelengths. Despite this limitation, many colorblind individuals develop enhanced abilities to detect subtle differences in brightness and texture. Some people have a 4th type of cone cell, making them tetrachromats who can potentially see millions more colors than typical humans. This condition is rare and occurs almost exclusively in women. Tetrachromats may be able to distinguish between colors that appear identical to everyone else, seeing subtle variations in shades that the rest of us cannot perceive. Animals across the natural world have evolved different color vision systems adapted to their specific needs and environments. Many birds can see ultraviolet light, revealing patterns on feathers and in flowers that are completely invisible to us. Bees can see ultraviolet but cannot see red, making their visible spectrum shifted towards shorter wavelengths compared to ours. Some fish and reptiles can see into the near-infrared, while many nocturnal mammals see primarily in shades of blue and green. The colors of objects in our world result from the complex interactions between light and matter. Most objects appear colored because they selectively absorb certain wavelengths while reflecting others back to our eyes. A red apple appears red because its skin contains pigments that absorb most wavelengths of visible light, while reflecting predominantly red wavelengths. The specific molecular structure of these pigments determines exactly which wavelengths are absorbed and which are reflected. Chlorophyll, the green pigment in plants, absorbs strongly in the red and blue portions of the spectrum while reflecting green light. This selective absorption allows plants to capture the energy they need for photosynthesis while giving them their characteristic green appearance. In autumn, as chlorophyll breaks down, other pigments become visible, creating the spectacular reds, oranges, and yellows of fall foliage. Some colors arise not from pigments, but from the physical structure of materials. The brilliant blue of a peacock's feathers comes not from blue pigments, but from microscopic structures that interfere with light waves, selectively reflecting blue wavelengths while cancelling out others. Similarly, the iridescent colors of soap bubbles, oil slicks, and beetle shells result from thin film interference, where light waves reflecting from different surfaces combine to enhance certain colors while suppressing others. Rayleigh scattering, the same phenomenon that makes the sky blue, also affects how we perceive colors in the atmosphere. During sunrise and sunset, sunlight must travel through much more atmosphere to reach our eyes. The atmosphere scatters away most of the blue light, leaving predominantly red and orange wavelengths to color the sun and surrounding sky. This scattering effect is why the sun appears yellow during the day rather than its true white color, and why it appears red when low on the horizon. The study of color has practical applications far beyond aesthetics. Astronomers use the colors of stars to determine their temperatures, compositions, and distances. Hot blue stars burn at temperatures exceeding 20,000 degrees Celsius, while cool red stars have surface temperatures of only a few thousand degrees. By analyzing the precise wavelengths of light emitted or absorbed by stars, scientists can identify the elements present in their atmospheres and track their evolution over billions of years. Color temperature describes the appearance of white light sources, measured in Kelvin. Candlelight appears warm and orange, with a color temperature of about 2000 Kelvin. while daylight appears cooler and bluer at about 6,000 Kelvin. LED lights can be manufactured to produce specific color temperatures, allowing us to create lighting that mimics natural sunlight or provides the warm glow of traditional incandescent bulbs. The technology of color reproduction in displays and printing relies on understanding how our eyes perceive color. Computer monitors and television screens use combinations of red, green, and blue light to create the full spectrum of colors we see on screen. Color printers typically use cyan, magenta, yellow, and black inks to absorb specific wavelengths from white light, creating colors through subtractive color mixing rather than the additive color mixing used in light-based displays. Lasers can produce extremely pure colors because they emit light at very specific wavelengths. A red helium neon laser emits light at exactly 632.8 nanometers, creating a red color more saturated and pure than any pigment could achieve. Green laser pointers, using frequency-doubled infrared light, produce green light at 532 nanometers, appearing exceptionally bright to our eyes because of our high sensitivity to green wavelengths. The future of color technology promises even more vibrant and accurate color reproduction. Quantum dots, tiny semiconductor particles, just a few nanometers across, can be engineered to emit very specific colors when stimulated by light or electricity. Television displays using quantum dot technology can reproduce a wider range of colors than traditional displays, creating more lifelike and vivid images. Understanding the relationship between wavelength and color also helps explain why certain combinations of colors appear harmonious, while others seem to clash. Color theory, developed by artists and scientists over centuries, describes how colors interact visually and emotionally. Complementary colors, which appear opposite each other on the color wheel, stimulate different sets of cone cells in our eyes, creating strong visual contrast and vibrant combinations. The wavelength of light even affects how colors appear under different lighting conditions. Metameric colors appear identical under one type of lighting, but different under another because they reflect different combinations of wavelengths that happen to stimulate our cone cells in the same way under specific illumination. This is why it's important to view fabric or paint samples under the same type of lighting where they will ultimately be used. The world is awash with color, but it is light that creates the palette, painting everything we see. Each color tells a story, a message encoded in the wavelength of light that connects us to the fundamental properties of matter and energy throughout the universe. As we continue our journey into understanding light, we will discover how these colored wavelengths interact with matter in ways that reveal even deeper mysteries about the nature of reality itself. When light meets matter, it changes, it bends, it is absorbed, it is reflected back to us. These interactions shape the world we see and reveal the fundamental nature of both light and the materials that surround us. Every surface, every object, every atom responds to light in its own unique way, creating the rich tapestry of colors, textures, and visual experiences that define our daily lives. The interaction between light and matter depends on the energy of the photons and the structure of the atoms and molecules they encounter. When a photon approaches an atom, several different outcomes are possible. The photon might be absorbed, transferring all its energy to an electron and disappearing completely. It might be reflected or scattered, bouncing away with its energy intact. Or it might pass through the material unchanged, as if the matter were not there at all. Absorption occurs when a photon carries exactly the right amount of energy to promote an electron from one energy level to another within an atom. Atoms have very specific energy levels, like steps on a staircase, and electrons can only exist at these particular energies. When a photon with the precise energy difference between two levels strikes an atom, the electron absorbs the photon and jumps to the higher energy level. This process explains why different materials absorb different colors of light. The absorbed energy does not simply disappear. In most cases, the excited electron quickly falls back to its original energy level, releasing the energy as heat or as new photons with different energies. Sometimes the electron falls back in stages, emitting several lower energy photons instead of one high energy photon. This process, called fluorescence when it happens quickly, or phosphorescence when it happens slowly, is responsible for the glow of fluorescent lights, the brightness of highlighter markers, and the eerie green glow in the dark materials. Transmission occurs when photons pass through a material without being absorbed. This happens when the photon energy does not match any of the energy differences between electron levels in the material's atoms. Glass appears transparent to visible light because the atoms in glass have energy level differences that correspond to ultraviolet wavelengths, well above the energy of visible photons. The visible light photons simply pass through the glass because they cannot interact with the electrons in any significant way. However, transparency is not absolute. The same glass that appears perfectly clear to visible light absorbs strongly in the ultraviolet range. This is why ordinary window glass provides some protection from sunburn, blocking the harmful ultraviolet photons while allowing visible light to pass through. Different types of glass can be formulated to block different wavelengths, creating materials that appear transparent to some types of light while being opaque to others. Scattering represents another important way that light interacts with matter. When light encounters particles or structures that are comparable in size to its wavelength, the light can be scattered in different directions without being absorbed. Rayleigh scattering occurs when particles are much smaller than the wavelength of light, and it affects shorter wavelengths more strongly than longer ones. This is why the sky appears blue, as the tiny molecules in Earth's atmosphere scatter blue light more effectively than red light. Mie scattering happens when particles are similar in size to the wavelength of light. This type of scattering affects all wavelengths more equally, which is why clouds appear white. The water droplets in clouds are large enough to scatter all visible wavelengths approximately equally, combining to create white light. When clouds become very thick, they can block so much light through scattering that they appear grey or black from below. The surface properties of materials dramatically affect how they interact with light. Smooth surfaces create specular reflection, where light bounces off at predictable angles, according to the law of reflection. This is what allows mirrors to create clear images and why still water can act like a perfect mirror on a calm day. Rough surfaces create diffuse reflection, scattering light in many different directions and making the surface visible from all angles. The roughness that determines whether reflection is specular or diffuse depends on the wavelength of light being considered. A surface that appears smooth to red light might seem rough to blue light because blue light has a shorter wavelength. This wavelength dependence is why some materials appear different colors when viewed under different types of lighting or from different angles. Metallic surfaces interact with light in unique ways because they contain free electrons that can move easily throughout the material. When light strikes a metal, these free electrons oscillate in response to the electromagnetic field of the light wave. This oscillation re-radiates electromagnetic waves, effectively reflecting most of the incident light. However, some energy is always lost to heat as the electrons collide with atoms in the metal, which is why metals feel warm when exposed to bright light. The color of metals depends on which wavelengths are absorbed and which are reflected. Silver and aluminum reflect most visible wavelengths equally, appearing silvery white. Gold absorbs blue and violet light while reflecting red, yellow, and green wavelengths, giving it its characteristic golden color. Copper absorbs most wavelengths except red and orange, which is why it appears reddish-brown. Semiconductors represent a special class of materials with properties between those of metals and insulators. In semiconductors, electrons need a specific amount of energy to jump from the valence band, where they are bound to atoms, to the conduction band, where they can move freely. This energy difference, called the band gap, determines which wavelengths of light the semiconductor can absorb. Silicon has a band gap that corresponds to near-infrared wavelengths, which is why silicon solar cells appear dark blue or black. They absorb visible light efficiently, converting the photon energy into electrical energy by promoting electrons to the conduction band. Gallium arsenide has a band gap corresponding to red light, making it useful for red LED lights and infrared laser diodes. The interaction between light and biological materials creates many of the colors we see in living organisms. Melanin, the pigment responsible for brown and black colors in skin, hair, and eyes, absorbs light across a broad range of wavelengths. The amount and type of melanin determines skin color and provides protection against harmful ultraviolet radiation from the sun. Hemoglobin, the protein that carries oxygen in red blood cells, absorbs green and blue light while reflecting red wavelengths. This selective absorption gives blood its red color and creates the reddish appearance of well-oxygenated skin. When hemoglobin releases its oxygen, its absorption spectrum changes slightly, which is why deoxygenated blood appears darker, red, or even bluish. Chlorophyll demonstrates one of the most important light-matter interactions on Earth. This green pigment absorbs strongly in the red and blue portions of the spectrum, while reflecting green light, giving plants their characteristic color. The absorbed light energy powers photosynthesis, the process that converts carbon dioxide and water into sugar and oxygen. Without this crucial interaction between light and chlorophyll, life as we know it could not exist on Earth. Carotenoids, another class of biological pigments, absorb blue and green light while reflecting yellow, orange, and red wavelengths. These pigments create the bright colors of carrots, tomatoes, and autumn leaves. In addition to their role in coloration, carotenoids help protect plants from damage by absorbing excess light energy that might otherwise harm the delicate photosynthetic machinery. Some organisms have evolved extraordinary ways to manipulate light through specialized structures rather than pigments alone. The brilliant blue color of a morpho butterfly's wings comes not from blue pigments but from microscopic structures that interfere with light waves. These structures, smaller than the wavelength of visible light, create constructive interference for blue wavelengths, while cancelling out other colors through destructive interference. Iridescence, the rainbow-like colors that shift and change with viewing angle, results from thin film interference or diffraction from regular structures. Soap bubbles display iridescent colors because light reflects from both the inner and outer surfaces of the soap film. The thickness of the film determines which wavelengths interfere constructively and which interfere destructively, creating the swirling patterns of color that dance across the bubble's surface. Polarization represents another way that light interacts with matter. Certain materials, like polarizing filters, selectively absorb light waves oscillating in one direction, while transmitting waves oscillating perpendicular to that direction. This selective absorption can dramatically reduce glare from reflective surfaces and enhance contrast in photographs and displays. Some materials exhibit birefringence, where light waves oscillating in different directions travel at different speeds through the material. This can split a single light beam into two separate beams traveling in slightly different directions, creating the double images visible through certain crystals like calcite. The temperature of materials affects how they interact with light. As objects heat up, their atoms vibrate more energetically, and they begin to emit light at wavelengths determined by their temperature. Cool objects emit primarily infrared radiation, while very hot objects like stars emit visible light and beyond. This thermal emission is how we can see hot metal glowing red in a forge or white hot in an electric furnace. Understanding how light interacts with matter has enabled countless technological advances. Optical fibers guide light through glass with minimal loss by using total internal reflection. Laser cutting and welding use intense light to heat materials to their melting or vaporization points. Photovoltaic cells convert light directly into electricity by using the photoelectric effect in semiconductors. Medical applications of light-matter interactions include everything from basic vision correction with eyeglasses to sophisticated procedures like laser surgery and photodynamic therapy. X-rays interact differently with various tissues in the body, allowing doctors to see inside patients without invasive procedures. MRI machines use radio waves to excite atoms in the body and detect the light they emit as they relax back to their normal state. Spectroscopy, the analysis of how materials absorb and emit light, has become one of the most powerful tools in science. By studying which wavelengths are absorbed or emitted by a material, scientists can identify its composition, temperature, density, and motion. This technique allows astronomers to analyze the composition of distant stars and galaxies, chemists to identify unknown compounds, and biologists to study the structure and function of complex molecules. When light meets matter, it changes, it bends, it is absorbed, it is reflected back to us. These interactions create the visual world we experience and provide windows into the fundamental structure of atoms, molecules, and the materials that make up everything around us. As we delve deeper into these interactions, we begin to see how light serves as both a tool for understanding matter and a bridge between the macroscopic world we observe and the quantum realm, where matter and energy merge into one unified reality. In the quantum world, light behaves in strange, mysterious ways. It transcends the simple idea of wave or particle, existing in both forms, each one offering us new insights into the universe. This quantum nature of light reveals that reality at its most fundamental level operates according to rules that challenge our everyday intuitions and open doorways to technologies that seemed like pure science fiction just decades ago. The quantum nature of light emerges most clearly when we examine individual photons and their interactions with atoms. Unlike the continuous waves of classical physics, quantum light comes in discrete packets of energy that cannot be subdivided. Each photon carries a specific, indivisible amount of energy, determined by its frequency. This quantization of energy represents one of the most profound discoveries in the history of science, revealing that energy itself has a granular, particle-like structure at the smallest scales. When a single photon encounters an atom, the interaction occurs in an instant, with no intermediate states. The photon either gets absorbed completely, transferring all its energy to an electron, or it passes by without any interaction at all. There is no gradual absorption, no partial transfer of energy. This all-or-nothing behavior demonstrates the fundamental quantum nature of light and matter interactions. The wave-particle duality of light becomes even more mysterious when we consider experiments with single photons. In the famous double-slit experiment, individual photons passing through two narrow slits create an interference pattern on a screen, just as we would expect from waves. However, this pattern emerges even when photons are sent through the apparatus one at a time, with each photon seemingly interfering with itself. This suggests that each individual photon somehow passes through both slits simultaneously, exploring all possible paths before reaching the detector. Even stranger, if we try to determine which slit the photon actually passes through by placing a detector at one of the slits, the interference pattern disappears. The mere act of observation changes the behavior of the photon, forcing it to choose a definite path and behave like a particle rather than a wave. This observer effect reveals that the quantum world does not exist in definite states until it is measured, a concept that continues to puzzle physicists and philosophers alike. Heisenberg's uncertainty principle places fundamental limits on what we can know about photons simultaneously. We cannot measure both the exact position and exact momentum of a photon at the same time. The more precisely we try to determine where a photon is, the less precisely we can know where it is going, and vice versa. This is not simply a limitation of our measuring instruments, but a fundamental property of quantum reality itself. This uncertainty principle explains why we cannot build a perfect light detector that captures every photon without disturbing it. Any attempt to measure light must involve some interaction that changes the light itself. This fundamental trade-off between knowledge and disturbance is built into the very fabric of quantum mechanics and affects every aspect of how light behaves at the quantum level. Quantum superposition allows photons to exist in multiple states simultaneously until they are measured. A photon can be polarized both horizontally and vertically at the same time, or it can travel along multiple paths simultaneously. Only when we make a measurement does the photon collapse into a definite state. This superposition principle is what allows quantum computers to process multiple possibilities simultaneously, potentially solving certain problems exponentially faster than classical computers. Quantum entanglement creates even more mysterious connections between photons. When two photons are entangled, measuring the properties of one instantaneously affects the properties of the other, regardless of the distance separating them. Einstein famously called this spooky action at a distance, because it seemed to violate the principle that nothing can travel faster than light. However, experiments have repeatedly confirmed that entangled photons really do exhibit this non-local connection. The process of creating entangled photons often involves sending a high-energy photon through a special crystal that splits it into two lower-energy photons. These daughter photons share a quantum connection that persists even when they are separated by vast distances. Measuring the polarization of one photon immediately determines the polarization of its entangled partner, no matter how far away it has traveled. Quantum entanglement has practical applications in quantum cryptography, where entangled photons can create unbreakable communication channels. Any attempt to intercept the photons necessarily disturbs their quantum state, immediately alerting the legitimate recipients that the communication has been compromised. This quantum advantage makes it theoretically impossible for eavesdroppers to listen in without being detected. The photoelectric effect, which helped establish the photon concept, demonstrates how quantum mechanics differs from classical expectations. When light shines on a metal surface, electrons are ejected only if the light frequency exceeds a certain threshold, regardless of the light's intensity. Bright red light cannot eject electrons from most metals, while dim ultraviolet light easily can. This frequency dependence makes sense only if light comes in discrete photon packets, each carrying energy proportional to its frequency. Stimulated emission, the process that makes lasers possible, represents another distinctly quantum phenomenon. When a photon with the right energy encounters an atom in an excited state, it can stimulate the atom to emit an identical photon. The two photons emerge with exactly the same energy, direction, and phase, effectively cloning the original photon. This process can cascade through billions of atoms in a laser, creating an intense beam of identical, synchronized photons. The quantum nature of spontaneous emission explains why atoms naturally emit light when their electrons fall from higher to lower energy levels. This emission is fundamentally random and unpredictable for individual atoms, even though the average behavior of large numbers of atoms follows predictable statistical patterns. We cannot predict exactly when a particular excited atom will emit a photon, only the probability that it will emit within a given time period. Quantum tunneling allows photons to pass through barriers that should classically be impenetrable. When light encounters a thin barrier, there is a small but finite probability that photons can tunnel through to the other side, even if they do not have enough energy to classically overcome the barrier. This effect is used in scanning tunneling microscopes and has applications in quantum electronics. The vacuum itself has quantum properties that affect light propagation. What we think of as empty space actually contains quantum fluctuations, virtual particle pairs that spontaneously appear and disappear on incredibly short timescales. These fluctuations can affect the propagation of light and create measurable forces between closely spaced conducting plates, an effect known as the Casimir force. Quantum field theory describes light as excitations in the electromagnetic field that permeates all of space. Photons are the quanta of this field, the smallest possible excitations that can exist. Just as ocean waves are disturbances in water, photons are disturbances in the electromagnetic field. This field-theoretic view helps explain how light can exhibit both wave and particle properties as different aspects of the same underlying quantum field. Zero-point energy represents the minimum energy that the electromagnetic field can possess, even in what we consider empty space. This energy cannot be extracted or used to do work, but it has measurable effects on the behavior of atoms and molecules. The zero-point fluctuations of the electromagnetic field contribute to the stability of atoms and affect the rates of spontaneous emission. Quantum coherence describes the degree to which photons maintain definite phase relationships with each other. Highly coherent light, like that from a laser, has photons that are synchronized in frequency, phase, and direction. Incoherent light, like that from a typical light bulb, consists of photons with random phases and directions. The coherence properties of light determine its ability to create interference patterns and carry information. Squeezed light represents an exotic quantum state where the uncertainty in one property of light is reduced below the standard quantum limit at the expense of increased uncertainty in another property. These squeeze states can improve the precision of optical measurements and have applications in gravitational wave detection and quantum communication. Quantum optics has enabled the development of single photon sources that can generate exactly one photon at a time, on demand. These devices are crucial for quantum information processing and quantum cryptography applications. Creating reliable single photon sources requires careful control of quantum mechanical processes in atoms, quantum dots, or other nanoscale systems. Photon number states represent pure quantum states of light with definite numbers of photons. A one-photon state contains exactly one photon, a two-photon state contains exactly two photons, and so on. These states are fundamentally different from classical light, which always contains statistical mixtures of different photon numbers. Creating and manipulating photon number states requires sophisticated quantum optical techniques. The quantum Zeno effect demonstrates how frequent measurements can freeze the evolution of quantum systems. If we measure a photon very frequently, we can prevent it from changing state, effectively stopping its quantum evolution. This counterintuitive effect has been observed experimentally and has potential applications in quantum information processing. Quantum interference between indistinguishable photons creates unique phenomena that have no classical analog. When two identical photons approach a beam splitter simultaneously, they always exit together from the same output port rather than splitting apart. This bunching behavior, completely different from classical expectations, demonstrates the bosonic nature of photons and their tendency to occupy the same quantum state. The quantum nature of light has revolutionized our understanding of information and computation. Quantum information theory shows that photons can carry information in ways impossible with classical systems. Quantum bits or qubits can exist in superposition states, allowing quantum computers to process multiple possibilities simultaneously. Photons are ideal carriers of quantum information because they interact weakly with their environment and can travel long distances while maintaining their quantum properties. Future quantum technologies promise to harness these strange quantum properties of light for practical applications. Quantum networks could connect quantum computers around the world using entangled photons transmitted through optical fibers or satellite links. Quantum sensors using squeezed light could detect gravitational waves with unprecedented sensitivity or measure magnetic fields with accuracy far beyond classical limits. In the quantum world, light behaves in strange, mysterious ways. It transcends the simple idea of wave or particle, existing in both forms, each one offering us new insights into the universe. As we continue to explore and understand these quantum properties, we unlock new possibilities for technology and gain deeper appreciation for the fundamental strangeness and beauty of the quantum realm that underlies all of reality. Light is the universe's storyteller. It carries the history of the cosmos, from the birth of stars to the distant echoes of the Big Bang. Every photon that reaches our eyes or our telescopes is a messenger from across space and time, carrying information about the most distant galaxies, the most violent cosmic events, and the fundamental structure of reality itself. Through light, we can peer billions of years into the past and witness the universe as it was when it was young. When we look up at the night sky, we are literally looking back in time. The light from the nearest star beyond our sun, Proxima Centauri, left that star over 4 years ago. The light from the Andromeda Galaxy began its journey toward us 2.5 million years ago, when our earliest human ancestors were just beginning to walk upright on the African savanna. Light from the most distant galaxies we can observe with our most powerful telescopes has been traveling for over 13 billion years, showing us the universe as it appeared when it was less than 1 billion years old. This time delay effect of light creates what astronomers call the observable universe, a spherical region around Earth from which light has had time to reach us since the beginning of the universe. The observable universe extends about 46 billion light-years in all directions, even though the universe is only about 13.8 billion years old. This apparent contradiction occurs because space itself has been expanding during the time light has been traveling toward us, stretching the distances and making the observable universe larger than we might initially expect. The cosmic microwave background radiation represents the oldest light in the universe that we can directly observe. This faint glow, detected by radio telescopes around the world, was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for the first atoms to form. Before this time, the universe was filled with a hot, dense plasma that was opaque to light. Electrons and protons existed separately, and any photons that tried to travel through this plasma were immediately scattered by the free electrons. When the universe cooled to about 3,000 degrees Celsius, electrons and protons finally combined to form neutral hydrogen atoms. This event, called recombination, made the universe transparent to light for the first time. The photons that were released during this cosmic dawn have been traveling through space ever since, cooling and stretching as the universe expanded around them. What began as visible and infrared light has been redshifted into the microwave portion of the electromagnetic spectrum. The cosmic microwave background provides a snapshot of the universe as it appeared during its infancy. Tiny variations in the temperature of this radiation, measured to be just a few millionths of a degree, represent the seeds that would eventually grow into the galaxies and galaxy clusters we see today. These temperature fluctuations reveal the distribution of matter in the early universe and provide crucial clues about the fundamental parameters that govern cosmic evolution. Stars serve as cosmic lighthouses, beaming information about their properties across vast distances. The color of a star tells us its surface temperature. Blue and white stars burn hot, with surface temperatures exceeding 10,000 degrees Celsius, while red stars are cooler, with temperatures of only a few thousand degrees. Yellow stars like our Sun have intermediate temperatures of about 5,500 degrees Celsius. The brightness of stars reveals their intrinsic luminosity and allows us to estimate their distances. Some stars appear bright because they are close to us, while others appear bright because they are intrinsically very luminous, even though they may be much farther away. By comparing a star's apparent brightness with its intrinsic luminosity, astronomers can calculate how far away it is, using light as a cosmic measuring stick. Spectroscopy, the analysis of starlight spread out into its component wavelengths, reveals the chemical composition of stars. Each element in a star's atmosphere absorbs specific wavelengths of light, creating dark lines in the spectrum called absorption lines. By identifying these lines, astronomers can determine which elements are present in stars and in what quantities. This technique has revealed that stars throughout the universe are made of the same elements we find on Earth, demonstrating the fundamental unity of matter across the cosmos. The Doppler effect allows us to measure the motion of stars and galaxies through the shifts in their spectral lines. When a star moves toward us, its light is compressed to shorter wavelengths, shifting toward the blue end of the spectrum. When a star moves away from us, its light is stretched to longer wavelengths, shifting toward the red end. By measuring these Doppler shifts, astronomers can determine the radial velocities of cosmic objects with remarkable precision. Edwin Hubble's observations of distant galaxies in the 1920s revealed that almost all galaxies are moving away from us, with more distant galaxies receding faster than nearby ones. This discovery led to the realization that the universe itself is expanding, with space stretching and carrying galaxies along with it. The relationship between distance and recession velocity, known as Hubble's law, provides a way to measure the age and size of the universe using light as our guide. Supernovae, the explosive deaths of massive stars, serve as standard candles for measuring cosmic distances. Type Ia supernovae, caused by the explosion of white dwarf stars that have accreted matter from companion stars, reach nearly the same peak brightness, regardless of their location in the universe. By comparing the apparent brightness of these supernovae with their known intrinsic brightness, astronomers can calculate their distances with high precision. Observations of distant supernovae led to one of the most surprising discoveries in modern cosmology. In the late 1990s, two independent teams of astronomers found that the expansion of the universe is accelerating rather than slowing down as had been expected. This acceleration implies the existence of dark energy, a mysterious form of energy that makes up about 70% of the universe and drives the cosmic expansion ever faster. Gravitational lensing demonstrates that light itself can be bent by gravity, as predicted by Einstein's theory of general relativity. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the gravity of the intervening mass bends the light's path, acting like a cosmic lens. This effect can magnify and distort the images of background galaxies, allowing us to study objects that would otherwise be too faint to observe. Strong gravitational lensing can create multiple images of the same distant object, arranged in rings or arcs around the lensing mass. These Einstein rings, named after the physicist who predicted them, provide dramatic evidence for the curvature of space-time. Weak gravitational lensing causes subtle distortions in galaxy shapes that can be measured statistically to map the distribution of dark matter throughout the universe. Gamma-ray bursts represent the most energetic explosions in the universe since the Big Bang. These brief flashes of high-energy light, lasting from milliseconds to minutes, release more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. The light from gamma-ray bursts has traveled from the most distant reaches of the observable universe, providing information about the first generations of stars and the early epochs of cosmic history. The study of variable stars, whose brightness changes over time, has provided crucial insights into stellar evolution and cosmic distances. Cepheid variable stars pulsate with periods that are directly related to their intrinsic brightness. By measuring the pulsation period of a Cepheid, astronomers can determine its true luminosity and calculate its distance. These stellar standard candles were crucial for establishing the distance scale of the universe and discovering its expansion. Binary star systems, where two stars orbit around each other, reveal stellar masses through the gravitational dance of their orbital motion. As the stars eclipse each other, the total brightness of the system varies in predictable ways that allow astronomers to determine the stars' sizes, temperatures, and masses. Some binary systems contain exotic objects like neutron stars or black holes, providing laboratories for studying matter under extreme conditions. Exoplanets, planets orbiting other stars, can be detected through the tiny dimming they cause when they pass in front of their host stars. The transit method has revealed thousands of exoplanets, from gas giants larger than Jupiter to rocky worlds smaller than Earth. The amount of dimming tells us the planet's size, while the orbital period reveals its distance from the star. Spectroscopic analysis of starlight filtered through exoplanet atmospheres can even reveal the chemical composition of these distant worlds. The search for signs of life on exoplanets relies on analyzing the light from their atmospheres for biosignatures, chemical indicators that might suggest biological processes. Oxygen and water vapor are considered promising biosignatures because they are produced by life on Earth and would be difficult to maintain in planetary atmospheres through purely geological processes. Future space telescopes will be capable of detecting these signatures in the atmospheres of Earth like exoplanets. Quasars, among the most luminous objects in the universe, are powered by supermassive black holes consuming matter at tremendous rates. The light from quasars has traveled billions of years to reach us, allowing us to study the universe when it was much younger and galaxies were still forming. The spectra of quasars show absorption lines from intervening gas clouds, providing information about the distribution and evolution of matter throughout cosmic history. The cosmic web, the largest scale structure in the universe, can be mapped using the light from distant galaxies and quasars. Galaxy surveys that measure the positions and distances of millions of galaxies reveal a foam-like structure, with galaxies concentrated along filaments, separated by vast voids. This structure reflects the gravitational influence of dark matter and provides tests of our understanding of cosmic evolution. Radio astronomy opened up entirely new windows on the universe by detecting radio waves from cosmic sources. Radio galaxies and quasars emit intense radio radiation, while pulsars, rapidly rotating neutron stars, sweep beams of radio waves across space like cosmic lighthouses. The 21-centimeter line of neutral hydrogen allows radio astronomers to map the distribution of gas throughout our galaxy and others. Infrared astronomy reveals cool objects and processes hidden from optical telescopes. Star-forming regions, shrouded in dust that blocks visible light, glow brightly in infrared wavelengths. Brown dwarfs, failed stars too cool to sustain nuclear fusion, emit primarily infrared radiation. Even the cosmic microwave background, the afterglow of the Big Bang, is detected in the infrared and microwave portions of the spectrum. X-ray and gamma-ray astronomy study the most energetic phenomena in the universe. Accretion disks around black holes heat matter to millions of degrees, causing it to emit X-rays. Supernova remnants, the expanding shells of gas from stellar explosions, glow in X-ray light for thousands of years. Gamma-ray bursts and active galactic nuclei produce the highest energy photons in the universe, carrying information about matter in the most extreme environments. Neutrino astronomy represents a new frontier in cosmic observation. These nearly massless particles interact so weakly with matter that they can travel straight through planets and stars without being absorbed. Neutrinos from the sun's core, produced during nuclear fusion reactions, provide direct information about processes occurring deep within our star. Neutrinos from supernovae arrive hours before the light because they escape immediately from the stellar core, while light takes time to work its way out through the star's outer layers. Gravitational wave astronomy, made possible by detecting ripples in space-time itself, complements traditional light-based observations. When black holes or neutron stars spiral into each other, they create gravitational waves that carry information about these extreme events. Combining gravitational wave detections with optical, gamma-ray, and radio observations provides a complete picture of cosmic catastrophes. The future of astronomy lies in multi-messenger observations that combine light across all wavelengths with gravitational waves, neutrinos, and cosmic rays. These different messengers provide complementary information about cosmic events, like detectives gathering evidence from multiple sources to solve a cosmic mystery. Each type of radiation or particle travels through the universe differently, carrying unique information about its source and the intervening space. Light is the universe's storyteller. It carries the history of the cosmos, from the birth of stars to the distant echoes of the Big Bang. Through these cosmic messengers, we have learned that we live in an expanding universe filled with dark matter and dark energy, where stars are born and die in spectacular explosions, where planets orbit distant suns, and where the elements that make up our bodies were forged in the nuclear furnaces of ancient stars. As our technology advances and our understanding deepens, light continues to reveal new chapters in the grand story of the universe. As we explore beyond the visible, the universe reveals itself to us in ways we never imagined. Light's journey is far from over. The future of light research promises to unlock mysteries that will revolutionize our understanding of the cosmos and transform the very fabric of human civilization. From quantum technologies that harness the strange properties of individual photons, to telescopes that will peer deeper into space than ever before, we stand on the threshold of discoveries that will reshape our view of reality itself. The next generation of space telescopes will extend our vision far beyond what current instruments can achieve. The James Webb Space Telescope, already revealing unprecedented details about the early universe, represents just the beginning of a new era in astronomy. Its infrared sensors can detect light from the first galaxies that formed after the Big Bang, showing us cosmic dawn when the universe emerged from its dark ages and the first stars began to shine. Future telescopes will push even further into the infrared spectrum, where cool objects and dust-shrouded regions become visible. These instruments will study the formation of planetary systems around distant stars, watching as dust and gas collapse to form new worlds. They will peer through the cosmic dust that obscures much of our galaxy's center, revealing the supermassive black hole that lurks at the heart of the Milky Way and the dense clusters of stars that orbit around it. X-ray astronomy will advance with more sensitive detectors capable of studying the most energetic phenomena in the universe. Next-generation X-ray telescopes will observe matter falling into black holes, trace the hot gas that fills galaxy clusters, and study the aftermath of stellar explosions with unprecedented detail. These observations will help us understand how the heaviest elements are created and dispersed throughout the universe, seeding future generations of stars and planets. Gamma-ray astronomy, studying the highest energy photons in the universe, will benefit from larger and more sophisticated detector arrays. These instruments will track gamma-ray bursts, the brief but incredibly powerful explosions that mark the deaths of the most massive stars. By studying these cosmic lighthouses, astronomers will probe the very edge of the observable universe and learn about conditions in the early cosmos when the first generation of stars lived and died. Gravitational wave astronomy, though not directly using light, will work in concert with traditional telescopes to create a new form of multi-messenger astronomy. When gravitational wave detectors identify colliding black holes or neutron stars, telescopes across the electromagnetic spectrum will swing into action, searching for the light produced by these cosmic catastrophes. This coordinated approach will provide a complete picture of some of the most violent events in the universe. The combination of different types of light observation will reveal connections and patterns invisible to any single wavelength. Radio waves will trace the magnetic fields threading through space. Infrared light will reveal star formation hidden by dust. Visible light will show the motions of stars and gas. Ultraviolet radiation will highlight hot, young stars. X-rays will expose high-energy processes, and gamma rays will capture the most extreme events. Together, these different forms of light will paint a comprehensive portrait of cosmic evolution. Quantum optics will revolutionize how we generate, manipulate, and detect light for both scientific and practical applications. Single photon sources, devices that can produce exactly one photon at a time on demand, will enable new forms of quantum communication and computation. These sources must control quantum mechanical processes with extraordinary precision, engineering the energy levels of atoms or the properties of quantum dots to emit photons with specific characteristics. Quantum entanglement will find practical applications in creating unbreakable communication networks. Pairs of entangled photons can carry information in ways that make eavesdropping impossible. Any attempt to intercept the photons necessarily disturbs their quantum state, immediately alerting the intended recipients that the communication has been compromised. Networks of quantum repeaters will extend these secure communications across continental distances, using the strange properties of quantum mechanics to guarantee privacy. Quantum computers will use photons as qubits, the fundamental units of quantum information. Unlike classical bits that can only be 0 or 1, quantum bits can exist in superposition states that are simultaneously 0 and 1 until measured. Photonic quantum computers will perform calculations impossible for classical computers, potentially solving problems in chemistry, materials, science, and cryptography that currently require enormous computational resources. Squeezed light, an exotic quantum state where uncertainty in one property is reduced below the fundamental quantum limit, will enhance the sensitivity of precision measurements. The Laser Interferometer Gravitational Wave Observatory already uses squeezed light to improve its ability to detect the tiny distortions in spacetime caused by passing gravitational waves. Future applications will include more sensitive atomic clocks, better magnetic field sensors, and improved biological imaging techniques. Metamaterials, artificially structured materials with properties not found in nature, will give us unprecedented control over how light behaves. These materials can bend light in impossible ways, creating cloaking devices that make objects invisible or lenses that focus light beyond the normal diffraction limit. Metamaterials operating at optical frequencies will enable new forms of microscopy, allowing scientists to see details smaller than the wavelength of light itself. Plasmonics, the study of how light interacts with free electrons in metals, will miniaturize optical devices to nanometer scales. Surface plasmons, collective oscillations of electrons that travel along metal surfaces, can confine light to dimensions much smaller than its wavelength. This technology will enable optical circuits as compact as electronic circuits, potentially leading to computers that process information using light instead of electricity. Photonic crystals, materials with periodic structures that control the flow of light, will create new possibilities for manipulating optical signals. These artificial materials can create photonic band gaps, regions of wavelength where light cannot propagate, effectively stopping light in its tracks. Other photonic crystals can slow light to a crawl or speed it up, providing new tools for optical communication and signal processing. Laser technology will continue advancing toward higher powers, shorter pulses, and more precise control. Femtosecond lasers, producing pulses lasting only quadrillionths of a second, can freeze molecular motion and study chemical reactions as they happen. Attosecond lasers, with pulses lasting billionths of a billionth of a second, will capture the motion of electrons within atoms, revealing the fundamental processes that govern chemistry and materials science. High-power lasers will enable new forms of nuclear physics research, creating conditions similar to those inside stars or during the Big Bang. These intense light beams can accelerate particles to high energies, study matter at extreme temperatures and pressures, and potentially achieve controlled nuclear fusion for clean energy production. The interaction between ultra-intense laser light and matter enters regimes where quantum electrodynamics effects become important, testing our understanding of fundamental physics. Adaptive optics will continue improving ground-based telescopes' ability to see through atmospheric turbulence. Advanced systems will use artificial stars created by laser beams to measure atmospheric distortion in real time, then adjust telescope mirrors thousands of times per second to create images as sharp as those from space telescopes. These systems will enable ground-based telescopes to achieve unprecedented resolution and sensitivity. Interferometry, combining light from multiple telescopes to create virtual instruments much larger than any single telescope, will reach new levels of sophistication. The Event Horizon Telescope, which captured the first image of a black hole's shadow, demonstrates the power of this technique. Future interferometric arrays will span continents or even extend into space, creating telescopes with the resolving power to see surface details on nearby exoplanets. Fiber optic technology will evolve to carry ever more information over longer distances with less loss. Hollow core fibers, where light travels through air rather than glass, will reduce signal delay and enable new applications in precision timing and quantum communication. Multi-core fibers will increase data capacity by carrying multiple independent signals through a single cable, supporting the growing demand for internet bandwidth. Optical computing will process information using light instead of electricity, potentially achieving much higher speeds and lower power consumption than electronic computers. Photons do not interact with each other as strongly as electrons do, making it easier to process multiple signals simultaneously without interference. Optical neural networks will mimic the parallel processing capabilities of biological brains, possibly leading to artificial intelligence systems with unprecedented capabilities. Biophotonics will use light to study and manipulate biological systems with increasing precision. Optogenetics, the technique of using light to control genetically modified neurons, will advance treatments for neurological disorders and deepen our understanding of brain function. Super-resolution microscopy techniques will image living cells with molecular-level detail, revealing how biological processes work at their most fundamental level. Medical applications of light will expand to include more precise diagnostics and less invasive treatments. Optical coherence tomography will provide high-resolution images of tissues without the need for surgery. Photodynamic therapy will use light-activated drugs to destroy cancer cells while leaving healthy tissue unharmed. Light-based sensors will monitor blood chemistry, brain activity, and other vital signs continuously and non-invasively. Solar energy technology will achieve higher efficiencies and lower costs through better understanding of how light interacts with materials. Perovskite solar cells and other emerging technologies will capture more of the sun's spectrum and convert it to electricity more efficiently. Concentrated solar power systems will use mirrors and lenses to focus sunlight, generating electricity even when the sun is not shining by storing energy as heat. Quantum sensing will use the strange properties of light to measure physical quantities with unprecedented precision. Quantum magnetometers using trapped atoms and laser light will detect magnetic fields millions of times weaker than Earth's magnetic field. Quantum gravimeters will measure tiny variations in gravitational acceleration, helping geologists find oil deposits or archaeologists locate buried structures. The search for extraterrestrial life will benefit from increasingly sophisticated analysis of light from exoplanet atmospheres. Next-generation telescopes will search for biosignatures, chemical indicators that might suggest biological processes on distant worlds. The detection of oxygen, water vapor, and other gases in alien atmospheres could provide the first evidence that life exists elsewhere in the universe. Laboratory astrophysics will recreate cosmic conditions on Earth using intense laser beams and sophisticated experimental setups. These experiments will test our understanding of how matter behaves in the extreme environments found in stellar cores, supernova explosions, and the vicinity of black holes. By comparing laboratory results with astronomical observations, scientists will refine their models of cosmic evolution and stellar death. Quantum gravity experiments will probe the intersection between quantum mechanics and general relativity using light. These experiments will test whether gravity affects quantum superposition, whether time dilation influences quantum decoherence, and other fundamental questions about the nature of spacetime. The results could guide the development of a theory of quantum gravity, one of physics' greatest unsolved problems. The study of dark matter and dark energy will benefit from more sensitive observations across the electromagnetic spectrum. Weak gravitational lensing surveys will map the distribution of dark matter by measuring tiny distortions in galaxy shapes. Observations of distant supernovae will track the acceleration of cosmic expansion and probe the properties of dark energy. These studies may reveal whether dark energy is truly constant or changes over time. As we stand on the threshold of these new discoveries, we realize that our journey into understanding light has only just begun. Each new technology, each improved instrument, each refined theory opens new questions and reveals new mysteries. The light that has guided human civilization from our earliest ancestors, gathered around fires, to the advanced technologies of today, will continue to illuminate the path toward an even more amazing future. As we explore beyond the visible, the universe reveals itself to us in ways we never imagined. Light's journey is far from over. From the quantum realm, where individual photons carry information through unbreakable codes, to the cosmic scale where light from the edge of the observable universe tells the story of creation itself. We are connected to the vast web of existence through the ancient and eternal language of light that speaks of wonder, discovery, and infinite possibility. Light is not just what we see, it is the fabric of the universe, shaping the cosmos and our lives. As we rest beneath the stars, we know that light, in all its forms, continues its journey through the universe, unveiling the mysteries of existence, one photon at a time. Tonight, as you settle into peaceful rest, take a moment to marvel at the extraordinary nature of light that surrounds you even in darkness. The gentle glow filtering through your window carries with it a story that spans the entire history of the universe. Each photon has traveled an incredible journey, perhaps from our sun across 93 million miles of space, or from distant stars, whose light began its voyage toward Earth before human civilization existed. The air around you is filled with invisible electromagnetic radiation, carrying information, energy, and the subtle quantum connections that bind the universe together. Radio waves from distant galaxies whisper of cosmic events that occurred billions of years ago. Infrared radiation from every warm object creates an invisible landscape of heat and energy. The cosmic microwave background, the afterglow of creation itself, bathes everything in the faint echo of the Big Bang. Even in the quietest darkness, light continues its eternal dance. Photons stream through space at the ultimate speed limit of the universe, carrying messages between distant worlds and connecting every corner of the cosmos in an intricate web of electromagnetic communication. These messengers of light have witnessed the birth of stars, the formation of planets, and the emergence of life itself. Your own body participates in this cosmic symphony of light. The calcium in your bones was forged in the nuclear furnaces of ancient stars, created when stellar cores reached temperatures hot enough to fuse lighter elements into heavier ones. The iron in your blood was scattered across space by supernova explosions, spectacular stellar deaths that briefly outshone entire galaxies. The carbon that forms the foundation of every living molecule was cooked in the hearts of massive stars during their final violent moments. These elements came together on our planet through processes powered by light from our sun. Photosynthesis, driven by visible light photons, created the oxygen you breathe and the food that sustains you. The warmth that maintains your body temperature ultimately comes from nuclear fusion reactions in the sun's core, where hydrogen atoms combine to create helium and release the energy that makes life possible. Your eyes, those remarkable biological instruments that have allowed you to see the world around you, represent the culmination of billions of years of evolution shaped by light. From simple light-sensitive spots in primitive organisms to the sophisticated cameras of modern animals, evolution has refined the ability to detect and interpret electromagnetic radiation. Your visual system can respond to individual photons, making it one of the most sensitive scientific instruments ever created. The colors you see in your memory of today, the blue of the sky, the green of trees, the countless hues that paint your world, all exist because of the quantum properties of light and matter. Each color tells a story about the atoms and molecules that created it, revealing the hidden quantum mechanical processes that govern reality at its most fundamental level. The red of a rose speaks of electron transitions in organic molecules, while the blue of the sky whispers of photons scattering off atmospheric particles. As you drift towards sleep, consider the incredible journey of discovery that has brought us to our current understanding of light. From ancient philosophers wondering about the nature of vision to modern physicists exploring quantum entanglement and gravitational waves, humanity has slowly unraveled the mysteries of electromagnetic radiation through careful observation, brilliant insights, and painstaking experimentation. Galileo's attempts to measure light speed with lanterns on hilltops, Newton's experiments with prisms revealing the spectrum hidden in white light, Maxwell's equations showing that light and electromagnetism are one phenomenon. Einstein's revelation that light comes in particle-like packets of energy, and countless other discoveries have built our modern understanding piece by piece, photon by photon. This understanding has transformed human civilization in ways our ancestors could never have imagined. Electric lights banish the darkness, allowing us to extend our active hours beyond the rhythm of day and night. Lasers perform delicate surgery, cut through steel, and carry information across continents through fiber optic cables. Radio waves connect us instantly with people around the world, while satellites relay signals from space to bring distant places into our homes. Medical imaging using X-rays, MRI, and other forms of electromagnetic radiation allows doctors to see inside the human body without surgery. Solar panels convert sunlight directly into electricity, promising a future powered by clean, renewable energy. Telescopes across the electromagnetic spectrum have revealed that the universe is far larger, older, and more magnificent than anyone once dared to dream. Yet for all our advances, light continues to surprise us with new mysteries and possibilities. Quantum mechanics has shown us that light behaves in ways that challenge our basic intuitions about reality. Photons can be in multiple places simultaneously, can be entangled across vast distances, and can exist in superposition states that defy classical description. These strange properties are not just academic curiosities, but the foundation for emerging technologies that will reshape our world. Quantum computers, using photons as qubits, may soon solve problems that are impossible for classical computers. Quantum communication networks will provide unbreakable security for sensitive information. Quantum sensors will measure physical quantities with unprecedented precision, opening new windows into the fundamental nature of space and time. Future telescopes will peer deeper into space and further back in time than ever before, showing us the universe as it was when the first stars were born and the first galaxies began to shine. We may finally answer the age-old question of whether life exists elsewhere in the universe by analyzing the light from distant exoplanet atmospheres, searching for the chemical signatures of biological processes. The continuing story of light is ultimately the story of human curiosity and ingenuity. Each generation builds upon the discoveries of those who came before, pushing the boundaries of knowledge ever further. The photons that warm your skin today have traveled the same path for billions of years, but our understanding of their nature continues to evolve and deepen. As you rest under the gentle touch of starlight, you are connected to the vast cosmos through the ancient language of light. The photons entering your eyes began their journey in nuclear furnaces burning at temperatures of millions of degrees, traveled through the cold vacuum of space for years or centuries or millennia, passed through Earth's atmosphere, and finally reached you to complete their cosmic voyage. In that simple act of seeing, you participate in one of the universe's most fundamental processes. Light and matter interact, quantum mechanical wave functions collapse, and information flows from the distant cosmos into your consciousness. You become a part of the vast network of electromagnetic radiation that connects every atom, every planet, every star in an intricate web of energy and information. The same physical laws that govern the behavior of light in your bedroom govern the light from the most distant quasars, the radiation from the cosmic microwave background, and the photons that carry signals between quantum computers. You are made of the same elements that shine in distant stars, governed by the same forces, connected through the same fundamental fields that permeate all of space. Tonight, as you close your eyes and allow sleep to come, know that you carry within you the legacy of billions of years of cosmic evolution. The atoms in your body remember their birth in stellar cores, their dispersal through space in supernovae explosions, and their gathering together on this small planet where they became part of something extraordinary, something capable of contemplating its own existence. Light will continue its journey long after we are gone, carrying information and energy across the cosmos, connecting distant worlds, and perhaps allowing other forms of consciousness to discover their own place in the magnificent tapestry of existence. The photons streaming past Earth tonight will travel for billions of years, some perhaps reaching civilizations we cannot yet imagine, carrying with them the same fundamental properties and possibilities that have shaped our own understanding. Rest now in the knowledge that you are part of something far grander than you can fully comprehend, connected through light to the deepest mysteries and greatest wonders of the universe. The cosmos surrounds you with its gentle radiation, the stars shine down with their ancient light, and the quantum realm hums with invisible possibilities that scientists are only beginning to explore. Light is not just what we see, it is the fabric of the universe, shaping the cosmos and our lives. As we rest beneath the stars, we know that light, in all its forms, continues its journey through the universe, unveiling the mysteries of existence, one photon at a time. Sleep well, knowing that tomorrow will bring new discoveries, new understanding, and new appreciation for the magnificent phenomenon we call light.